Hello everyone. Today I am going to discuss part 22 lecture of electrochemistry and following topics will be discussed in this lecture. The topics are activity for a component in electrolyte solution, mean activity of an electrolyte, mean ionic molality, activity coefficient. Now see the first slide. Activity for a component in electrolyte solution. The activity is more complicated in electrolyte solutions than in solution of non-electrolyte because it dissociates into ions and exhibit marked deviation from ideal behavior even at low concentration. That is the problem for an electrolyte because electrolyte dissociates into ions. Okay. Now consider an electrolyte like this AXBY that dissociates in solution like this XAY plus YBX minus. So AY plus is the cation and BX minus is the anion. Number of cation is X, number of anion is Y. So here you can see that this electrolyte it dissociates into its corresponding ion. That's why it is very difficult to measure the activity of the individual ions. So always you have to measure the mean activity. Now consider the chemical potential of this electrolyte AXBY is equal to mu AXBY. Now according to Lewis formula of activity, you can write mu AXBY is equal to mu 0 AXBY plus RT ln A AXBY. So AXBY is the activity of AXBY electrolyte. Now we can also write mu AXBY is equal to X mu of the cation. So X into mu AY plus Y into mu BX minus. Therefore, you can write X into mu 0 AY plus chemical potential, standard chemical potential of the cation plus RT ln activity of the cation plus Y into mu 0 of anion plus RT ln activity of the anion. Therefore, you can write X mu 0 cation plus Y into mu 0 of anion plus RT X ln activity of the cation plus Y ln activity of the anion. So you can write X mu 0 of cation plus Y mu 0 of anion, that is equal to mu 0 AXBY standard chemical potential plus RT ln activity of cation to the power X plus ln activity of anion to the power Y. And finally you can write mu 0 AXBY plus RT ln activity of cation to the power X, activity of anion to the power Y. Now if you compare equation number 1 and equation number 2, you can say that activity of the electrolyte AXBY equal to activity of the cation to the power X, activity of the anion to the power Y. Okay, so this is the formula of activity of an electrolyte. So in general, for any electrolyte, you can write activity is equal to activity of cation. Here A plus means the activity of the cation to the power number of the cation. Here you can see X is the number of cations. So you can write activity of the cation to the power number of the cations into activity of the anion to the power number of anions. So here A is equal to activity of electrolyte, A plus activity of cation, A minus activity of anion, X is equal to number of cations, Y is equal to number of anions. Now you have to consider what is mean activity of the electrolyte, and here you can see it is represented by A plus minus. Already I have told you that individual activities of cations and anions cannot be determined. So it is more appropriate to express the activity for a component in electrolyte solution in terms of mean activity of the electrolyte. Okay, the mean activity is the geometric mean of individual ion activities. So always remember, mean ionic activity is the geometric mean of the individual ion activities. Let total number of moles of ions produced by 1 mole of electrolyte be nu. So here you can see nu is the total number of ions, or you know that x is equal to number of cations and y is equal to number of anions. So you can write nu is equal to x plus y, total number of ions. So mean ionic chemical potential mu plus minus is defined by nu into mu plus minus equal to x into mu plus y into mu minus. So this is equation number 4. So mu plus minus, that is mean ionic chemical potential into number of total ions, is equal to x mu plus y into mu minus. Now chemical potential for any electrolyte mu is equal to x into mu plus y into mu minus. This is equation number 5. Hence you can write mu is equal to nu into mu plus minus. Okay. Now mean ionic chemical potential mu plus minus equal to mu plus minus 0 standard mean ionic chemical potential plus RT ln A plus minus. Now you can see new term here, A plus minus. A plus minus equal to mean ionic activity. Now as you seen here, mu is equal to nu into mu plus minus, mu is equal to nu into mu plus minus. So how you can write? Mu means mu 0 plus RT ln A, that is equal to nu into mu plus minus. Now you see mu plus minus is equal to mu plus minus 0 plus RT ln A plus minus. So put the value of mu plus minus here. So that is equal to nu into mu plus minus 0 plus nu RT ln A plus minus. Now from that equation you can say that mu 0 is equal to nu into mu plus minus 0, that is equal to x into mu plus 0 plus y into mu minus 0. So from that equation you can write RT ln A is equal to nu RT ln A plus minus. So from that equation you can write A is equal to A plus minus to the power nu. This is equation number 7. So in general, for any electrolyte, you can write activity of the electrolyte A is equal to A plus to the power x, A minus to the power y, that is equal to A plus minus to the power x plus y, or A plus minus to the power nu. So A is equal to activity of the electrolyte, A plus is equal to activity of cation, A minus is equal to activity of anion, A plus minus is equal to mean ionic activity, x is equal to number of cations, and y is equal to number of anions. Now see the next slide. Activity in terms of molality. Remember, in electrolyte solution, the concentration is expressed in terms of molality. Okay. Now you have to know what is the relationship between activity and molality. First consider activity of cation. Activity of cation is represented by A plus, that is equal to M plus divided by M0 into gamma plus. So here you can see M plus. M plus is equal to molality of cation. M0 is equal to standard state molality and is equal to 1 mole per kg. So how you can write? A plus is equal to M prime plus into gamma plus. So M prime plus is equal to M plus divided by M0. Okay. And gamma plus, here you can see new term, gamma plus is called activity coefficient of cation. So for a single ion, you can write activity of the ion is equal to concentration of the ion into activity coefficient. Now consider for an anion, activity for an anion. So A minus is equal to the activity of anion, that is equal to M minus divided by M0 into gamma minus. So here you can see again M minus is equal to molality of anion. M0 is equal to standard state molality and is equal to 1 mole per kg. So how you can write M minus is equal to M minus prime into gamma minus. So M prime minus is equal to M minus divided by M0 and gamma minus is equal to activity coefficient of anion. So again you can see for anion, activity of the anion is equal to concentration of anion into activity coefficient. Similarly, mean ionic molality Ma plus minus equal to M prime plus minus into gamma plus minus. So gamma plus minus equal to mean ionic activity coefficient. Now you know that A plus minus to the power nu is equal to A plus to the power x, A minus to the power y. And A plus minus is equal to M prime plus minus into gamma plus minus. So put the value here. M prime plus minus into gamma plus minus to the power nu equal to A plus means M prime plus into gamma plus to the power x, and A minus is equal to M prime minus into gamma minus to the power y. So you can write M prime plus minus to the power nu is nu into gamma plus minus to the power nu equal to M prime plus to the power x, M prime minus to the power y, gamma plus to the power x, gamma minus to the power y. Now if you consider this equation, from that equation you can write mean ionic molality M prime plus minus equal to M prime plus to the power x, M prime minus to the power y to the power 1 by nu, and mean ionic activity coefficient gamma plus minus equal to gamma plus minus to the power x, gamma minus to the power y to the power 1 by nu. Okay. Therefore, like mean ionic activity, M prime plus minus and gamma plus minus are also geometric means of the individual ionic quantities. Therefore, you write molality of electrolyte M prime equal to M prime plus minus to the power nu, and M prime plus minus to the power nu means you can write M plus to the power x and M prime minus to the power y, and activity coefficient gamma equal to gamma plus minus to the power nu equal to gamma plus to the power x into gamma minus to the power y. Okay, so this is the molality of electrolyte and this is the activity coefficient. Now for any electrolyte, M prime plus is equal to x into M prime. M prime is the concentration of the electrolyte and M prime plus is the concentration of the cation, and x is equal to number of cations. So you can write M prime plus is equal to x into M prime and M prime minus is equal to y into M prime. So how you can write M prime plus minus to the power nu equal to x M prime to the power whole to the power x and y M prime whole to the power y. So you can write x to the power x, y to the power y, M prime to the power x plus y. Therefore, M prime plus minus equal to x to the power x, y to the power y whole to the power 1 by nu, nu means x plus y, into M prime. That is the relationship between the mean ionic molality and molality of an electrolyte, and that depends on the number of cations and number of anions. Now, what is the activity of an electrolyte? Activity of an electrolyte, A is equal to A plus minus to the power nu, and A plus minus to the power nu means M prime plus minus into gamma plus minus whole to the power nu, and already you have calculated what is the value of M prime plus minus to the power nu. So you can write that is equal to x to the power x into y to the power y, M prime to the power x plus y into gamma plus minus to the power x plus y. So that is the relationship of activity and molality of an electrolyte. And again, you can notice here that the activity of an electrolyte depends on the number of cations, number of anions, and mean activity coefficient of the electrolyte. Now consider some examples. Example for the determination of mean ionic activity M prime plus minus in terms of M prime. So you know this is the formula of M prime plus minus equal to x to the power x into y to the power y to the power 1 by nu into M prime. Now consider first number 1 point 1:1 electrolyte, and you know that the examples of 1:1 electrolytes are HCl, NaCl, KCl, etc. Now consider HCl. HCl produces H plus cation and Cl minus anion, and number of cation is 1, number of anion also 1. So you can write x is equal to 1 and y is equal to 1. Now put the value of x and y in this equation. You can write M prime plus minus equal to x to the power x, y to the power y to the power 1 by nu into M prime. So put the value of x 1 to the power 1, 1 to the power 1 whole to the power 1 by 1 plus 1 into M prime. So that is equal to M prime. So for 1:1 electrolyte, you can say that the mean ionic molality equal to the molality of the electrolyte. Now consider 2:2 electrolyte. For example, MgSO4. So MgSO4 dissociates into Mg2 plus cation and sulfate anion. So you can see number of cation x is equal to 1, number of anion y is equal to 1. So you can write M prime plus minus equal to 1 to the power 1 into 1 to the power 1 whole to the power 1 by 1 plus 1 into M prime, that is equal to M prime. So again for 2:2 electrolyte you can write the mean ionic molality is equal to the molality of the electrolyte. Now consider 2:1 electrolyte calcium chloride. So calcium chloride dissociates into calcium 2 plus ion and 2Cl minus anion. So here you can see number of cation x is equal to 1, number of anion y is equal to 2. Now put the value of x and y in this equation. M prime plus minus equal to 1 to the power 1, 2 to the power 2 whole to the power 1 divided by 1 plus 2 into M prime. So that is equal to cube root of 4 into M prime, that is equal to 1.587 M prime. So for 2:1 electrolyte, the mean ionic molality is not equal to the molality of that electrolyte. In that case, M prime plus minus equal to 1.587 M prime. Now consider 1:2 electrolyte Na2SO4. Na2SO4 produces 2 Na plus plus SO4 2 minus. So here you can see x number of cation is equal to 2, y number of anion equal to 1. So what you can write M prime plus minus equal to 2 to the power 2 into 1 to the power 1 whole to the power 1 divided by 2 plus 1 into M prime. So that is equal to cube root of 4 into M prime. So again it is 1.587 M prime. So for 1:2 electrolyte, the mean ionic molality M prime plus minus equal to 1.587 M prime. Now remember, in every examples, the 1:1 represents the charge of cation and charge of anion. So here you can see charge of cation is 1, charge of anion is 1. That is what is 1:1. 2:2 electrolyte means charge of cation is 2. Here charge of cation is 2, so 2:2. 2:1, here charge of cation is 2 and 1 is equal to charge of anion. And here I can see 1:2, charge of cation is 1 and charge of anion is 2. That's why it is 1:2 electrolyte. Now example for the determination of activity A in terms of M and gamma plus minus. So it is M prime actually in terms of M prime and gamma plus minus. So A is equal to A plus minus to the power nu is equal to M prime plus minus into gamma plus minus whole to the power nu. So you can write x to the power x, y to the power y, m prime to the power x plus y, and gamma plus minus to the power x plus y. Now see the first example, 1:1 electrolyte. HCl produces H plus and Cl minus ion. X is equal to 1, y is equal to 1. So you can write A is equal to 1 to the power 1 into 1 to the power 1, m prime to the power 1 plus 1, and gamma plus minus to the power 1 plus 1. That is equal to m prime to the power 2 and gamma plus minus to the power 2. Okay, so for 1:1 electrolyte, activity is equal to m prime square gamma plus minus square. Now consider 2:1 electrolyte, calcium chloride. Total charge of calcium 2 plus is 2 and charge of anion is equal to 1. So it is 2:1 electrolyte. Now you can see here number of cation x is equal to 1, number of anion y is equal to 2. So what I can write, activity A is equal to x to the power x, y to the power y, m to the power x plus y, gamma plus 1 to the x plus y. So put the value of x plus y in this equation. You can get 1 to the power 1 to the power 2, m prime to the power 1 plus 2, gamma plus minus to the power 1 plus 2. That is equal to 4 m prime cube into gamma plus minus cube. Now consider 3:1 electrolyte. AlCl3 produces Al3 plus cation and 3Cl minus anion. So x is equal to 1 and y is equal to 3. So what I can write, A is equal to 1 to the power 1, 3 to the power 3, m prime to the power 1 plus 3, gamma plus minus to the power 1 plus 3. That is equal to 27 m prime to the power 4, gamma plus minus to the power 4. So that is the 3:1 electrolyte. In that case, you can see the activity is equal to 27 concentration of the electrolyte to the power 4 into activity coefficient to the power 4. So these are the examples for the determination for this is not mean ionic activity, this is mean ionic molality m prime plus minus and it is activity. So these are the examples for the determination of mean ionic molality here and activity of an electrolyte. Next, you have to know molecular interpretation. First, see the diagram. Here you can see the positive charge. This is the cation and this is the anion. So you can consider NaCl dissociates into in solution corresponding its ions, sodium plus cation and Cl minus anion. But you can see in the dotted circle, this positive charge and negative charge produces an intimate or tight ion pair. And for that intimate ion pairs, the number of active cations and anion in the solution decreases. So what you can conclude? Some of the cations and anions form intimate ion pairs, see in the dotted circle, because of strong electrostatic attraction. As a result, the effective number of cations and anions in solution decreases. Therefore, all cations and anions in solution are not active. Thus, the effective concentration of the ions becomes less than the actual concentration. Thank you.